Okay, so up next we're getting to 8.2. So for 8.2, we're actually going to be doing the same thing. The only thing is we're transitioning from having a sample mean to now where we're going to be doing, we're going to be having something called a p-hat. So instead of doing a sample mean, we're going to be doing a sample proportion. So we're going to be having a sample proportion. And if you kind of look at it, it has something on top of the P. They usually call that hat. So technically, this is called the P hat. If you have the notes, I actually describe it right here in the notes. So what we're gonna be doing, we're gonna kind of be switching over. We're still gonna be doing exactly the same thing. The only thing we're gonna be doing, instead of doing this for the sample me, now we're doing this for a sample proportion. So first thing we kind of want to know is how do we find the sample proportion? So the formula for the sample proportion is this one. P hat is equal to x divided by n, where x is pretty much just a characteristic. So x is just whatever characteristic that you're looking for. So kind of think about it, say if I want to find the probability of male in the classroom, all I have to do is p hat is equal to male in the classroom. And you just want to divide it by total students. So x is represent which characteristic are you looking for. So in this case, or this example that I gave you, I'm telling you the characteristic that I'm looking for is that the student has to be a male, and you just want to divide it by the total amount of people or the total amount of students you have in the classroom. So that's how you're gonna find p hat. It is x divided by n. Any question in regard to that formula? So let's go over these three bulletin points. So if you look at the shape, so when we're looking at the shape, we're talking about does it have like a normal distribution, does it have a skew distribution, so on and so forth. So for this one, if the shape, kind of going back to the central limit theorem, because this is what we're referring to when we're talking about the shape. If you look at the shape, it says as the size of the sample n increase, the shape of the sampling distribution, the sample proportion become approximately normal. So that's pretty much our central limit theorem. So you're saying as n is increased, it's gonna tell us we have an approximately normal distribution. There's actually gonna be a different condition that you check because for 8.1, we use this condition that n has to be greater than or equal to 30. But for 8.2, we're going to use a different one. And once we actually get to that, so just remember for the central limit theorem, there are going to be two different central limit theorem. The only thing different is the condition, but the result is still the same. The central limit theorem, we're trying to use it to see if our data set could be approximately normal. All right, so let's go to the second bulletin point. So the second bulletin point says the standard, the mean sampling distribution of the sample proportion is equal to the population proportion, P. So when we talk about P, this is our population proportion. So if you ever see in the formula where it says P, P is just going to stand for population proportion. So right now we have P, that's population proportion. But we also have P hat, which is sample proportion. So you do want to kind of know the difference between P and P hat because it is going to help you with the problem. All right, so if you have P, P corresponds to population proportion. If you have P hat corresponds to your sample proportion. So just know the difference so that way in a formula, when it asks you for those two information, you know exactly what to put. All right, everybody good for the second bulletin point? All right, so the third one, it said the spread. So it's saying the standard deviation of sampling distribution of the sample proportion decreases as the sample size and increases. So pretty much the third one is saying the bigger the sample size you have, the smaller the spread you're gonna have. The smaller your sample size is, the bigger the spread is gonna be. And that's kind of going back to what we did last week. Because if you look at standard error, it is saying if you have a sample size of 1 compared to a sample size of like 100, the sample size of 100 should give you a more accurate reading versus a sample size of 1. A sample size of 1 should give you a less accurate reading. All right, but that's it for those 3 bulletin points. Any question in regard to any of those 3 bulletin points? All right, so let's go ahead and let's look at the simulation. All right, so hopefully the simulation got a little bit better than the last one we did last week. All right. So what we're gonna do for the simulation, so if you look at it, this is essentially like a candy jar or candy dispenser, and it has Reese's Pieces. So what we wanna do, we wanna find out what the population proportion of these Reese's Pieces is. So what we wanna do, we wanna take a sample size of pretty much of these Reese's Pieces. So what we're gonna start doing, we're gonna start sampling from this jar or from this dispenser. So what we wanna see, we wanna see what happened to the accuracy of our of our sample as we increase the sample size. So what we're gonna first do, when we have a sample size of 2, then we're gonna increase it to 10, then we're gonna increase it to 20, 30, 40. And we're gonna see what's happening to our accuracy. Is it going up or is it going down? All right. All right. So for this one, we already know pretty much the answer should be the probability of getting an orange Reese's Pieces should be 0.40. But let's act like we don't know that information, and let's just go purely on the sample size. So we're gonna say number of candies. So we're gonna say we're taking 2 candies, and let's do this real quickly. So what we're gonna do, we're gonna randomly select 2 candy from this dispenser. And what we wanna do, we just wanna record what proportion of the 2 candy were orange. So let's do this one time. All right, so if you look at it, we got 1 orange and 1 yellow, so we got 50%. So if you look at in the bottom, it says P hat is equal to 0.50. So the reason why it says P hat because, and why it says equal to 0.50, if you look at it, the characteristic that we're looking for is that the candy has to be orange. And then you divide it by however many total candy we selected. So since we have 1 orange and we selected 2 candy, is 1 divided by 2, which is 50%. Everybody kind of good with that? first simulation? Okay, so let's do a second simulation. And if you look in the bottom, they have that recording right here in 0.50. So I'm gonna do that again. So we'll do another random sample of 2 Reese's Pieces. And
Do
we
we have to use that website?
no, right now you just have to follow along to like what am I doing.
Okay.
Right. So right now what I'm gonna do a random sample of 2 Reese's Pieces again. And what I wanna do, I wanna record what proportion of them were orange. So let's do another sample. Oh, all right, so if I do another drawing of 2 Reese's Pieces, we get another orange and another yellow. So once again, we get 50%. So let's do that again. All right, so we get another 50%. So if you notice right here, it had 3 dots. It's to signify that we did this 3 times and all 3 times came up 50%. So we do that again. All right, so we finally got something different. We finally got 2 yellows. So it was saying 0% of them are yellow. So kind of to speed this up, I'm gonna do this 96 more times. So we did this a total of 100 times. So if you look at it, which one gather more sample, 0, 0.50, or 1? Yeah, so if you look at 0.50, actually has a higher proportion that the candy landed on 0.50. So that's kind of telling us that P is somewhere near 0.50. But if you look at the range, what's the lowest possible value based off of this graph that we have? Well, if you look at the lowest possible value, it's 0. So, and if you look at the highest possible value, it's 1. So telling us the range is anywhere from 0 to 1. So if you look at that range, it's not that good of a range because it's telling me it could be anywhere from 0 to 100%, which we kind of already knew it could be anywhere from 0 to 100%. So what we kind of want to go ahead and do, we kind of want to get a more accurate reading. So what I'm going to go ahead and do, we're going to increase the number of candy that we select. So I'm going to increase it from 2, and we're going to go to 4. So we'll say 4 random selection, and we'll do this 100 times. So I want to see if I can narrow it down and get a narrower range from 0 to 1. Hopefully, probably like 0.25 to 0.75. Let's go ahead and see what happens. So we'll say draw a sample. Oops. So if you look at it now we get that, okay, it could be 0%, 0.25%, 0.50, 0.75, and 1. So it's giving us more option now. So giving us more option of what it could possibly be. Because before, we only had 3 options. We had that could be 0%, 50%, to 100%. But now it's giving us more option, and that's because we're taking a bigger sample size. So it kind of just showing you the bigger sample size you take, the more option it's gonna give us. And if you look at it now 0.25 is kind of like the main leader. But we already know it should be 0.40. So, but if you look at a 0.50, it also has kind of like a big bar. So what we're gonna go ahead and do now, we're gonna start increasing this to, let's say, 10. And we're gonna see how does that affect our distribution. All right. So if you look at it now, which of these options has the bigger, will have the highest stop loss?
like 4 or 40%.
Yeah, 0.40. If you look at it, that one has the highest one. And if you look at it, the probability of it being orange should be 0.40. So we should start getting closer and closer to 0.40. But also kind of look, now we finally go from 0 to 80%. We're finally not doing 0 to 100%. So we're narrowing it down, and that's kind of going back to your standard error, because your standard error is telling us the bigger the sample size is, the narrower the spread should be. But let's kind of go crazy, and let's change it from number of candy from 10, and let's do 100. So we'll do draw sample. So we're gonna do this 100 times. All right. So if you look at it, it's still kind of centered somewhere in 0.40. But if you now look at the range, the lowest value that we possibly have is somewhere like I don't know, 0.30. And the highest value that we have is 0.52. So you kind of notice how the range got narrower because we take a bigger sample size. So you kind of showing you back with like the central, well, back where if you have a bigger sample size, the more accurate it should be because your standard error is technically going down. Because the bigger your sample size, the smaller your standard deviation should be. Because since we're dividing by that square root of n, it should start getting lower and lower. Cool. All right, so we're gonna do one more simulation. So we're gonna do this for 1,000. So this might take a little bit longer. So
I have a question.
yeah,
Are we gonna have test corrections for the final?
no. Yeah, final is final.
Okay.
All right, so hopefully this will finish up in the next 30 seconds or so.
This is just kind of a proof of concept. We're not going to need to access this for a test.
No. Yeah, this is like a proof of concept.
How much percentage of our grade is the final worth?
For that one, go check the syllabus. The syllabus should be on Canvas.
Okay.
All right, so hopefully I'll finish up pretty soon. Also, while I have this time, there are some tables you're gonna need for once we get to chapter 9. I actually already uploaded them onto Canvas, and they should be under the first module. It should say table, and it should say T table, new, and type table. So once we get to chapter 9, you're gonna be needing those 2 tables. So we should be getting to chapter 9 by Wednesday. So just make sure if you don't have a printer, have them available to you on your computer. So that way you could just pretty much have them ready. So that way once we start using them, you could just follow along. But yes, have the T table and the chi-square table. Well, we're probably not gonna use the chi-square table probably until next week, but you do need the T table for next Wednesday. All right, so let's look at this new distribution. So let's kind of zoom in on it. So if you look at it, it's still kind of narrowing down. Because if you look at the middle portion, you could kind of see it's still at 0.40, which makes sense because we already knew that the population proportion of orange candy was 0.40. So we should already know it will hover around 0.40. But if you look at what happened as I increased the sample size from 100 to 1,000, we got a narrower spread. So if you look at it now, the lowest value that we get is 0.36. And now the highest value that we got from this distribution is 0.44. So that's kind of showing you like how a bigger sample size, it could give you a more accurate reading. Because if I have a sample size of say 2 versus a sample size of 1,000, the sample size of 2 was telling me it could be anywhere from 0 all the way to 100%. But now that I have a sample size of 1,000, the sample size of 1,000 is narrowing it down and now telling me it could be anywhere from 0.36 all the way to 0.44. So that's what we're going to be working with for 8.2. So for 8.2, we're going to be working with proportion, and where you're going to see how likely we are to get a certain proportion given our sample size. All right, but that's kind of like an illustration of the sampling distribution for proportional data set. Any question in regard to this so far? All right, so let's go ahead and let's go back to the notes. All right. So if you kind of remember from chapter 8.1, we had mu of x bar, and we also had sigma of x bar. So mu of x bar was equal to mu, sigma of x bar was equal to sigma divided by square root of n. So for this chapter, we're also going to have that. So we're going to have a mu and a sigma, but instead of it being mu of x bar, it's going to be mu of p hat. So mu of p hat is equal to the population proportion. So if I ask you for mu of p hat, that's what I'm asking for. I'm just asking for the population proportion, which is equal to p. Also, there's a new formula for, because if you look at this one, this is sigma of x bar. This is sigma of p hat. So sigma of p hat is equal to this, and let's kind of blow it up for you. So sigma of p hat is equal to square root of p times 1 minus p divided by n. And that's how we're going to calculate our standard deviation. So for standard deviation of a sample proportion, we're going to take the square root of p times 1 minus p divided by n. Any question in regard to mu of p hat or sigma of p hat? All right, so up next, we're going to go into the new condition for the central limit theorem. So for this one, for the central limit theorem, we're only going to focus on the second condition. So we're only going to focus on the second condition for the central limit theorem. So for the central limit theorem for a sample proportion, it's a little bit different from the central limit theorem from a sample mean. So for the sample mean, n has to be greater than or equal to 30, and that was the rule for all cases. If n was bigger than or equal to 30, pretty much we're going to say is approximately normal. But unfortunately for the sample proportion, it kind of depends on what your proportion is or what your population proportion is. Because depending on how rare or how unrare that event is of occurring, you're actually going to need a bigger sample size or a smaller sample size. So say, well, let me tell you the formula, and then we'll kind of do some example. So the formula, you say you get n, you multiply by p, you multiply that by 1 minus p, and that has to be greater than or equal to 10. So that's how we're going to figure out if we should be able to apply the central limit theorem. If we do n times p times 1 minus p, it has to be greater than or equal to 10. All right. Any question in regard to, yes, the formula? All right. So now what I'm going to do, I'm going to show you why you kind of always have to look at your p, because depending on your p, it kind of dictate whether you need a bigger sample size or if you need a smaller sample size. So let's do an example where p is equal to 0.50. So if my population proportion is equal to 0.50, for this one, like, do you think I'm gonna need a lot of sample, or do you think my sample size should be pretty huge? Well, if you have p is equal to 0.50, is that something that like happen every once in a while, or that's something that you have to wait a long time for it to occur?
Every once in a while, half the time, right?
Yeah, half the time. So it should happen for very regularly, correct? So for this one, what we're gonna say a sample size of 40. So if I have a sample size of 40, I want to see if that's big enough. So what we're going to do, we're going to go ahead and use the formula for the central limit theorem. So we're going to do n times p times 1 minus p. So if I do n, that's 40. If I do p, that's 0.50. If I do 1 minus p, or 1 minus 0.50, so I'm going to go ahead and work that out on my TI-84. So let me turn it on. So we'll say 40 times 0.50 times parenthesis 1 minus 0.50. So if you look at it, we get exactly 10. So then you could go 10 is greater than or equal to 10. So in this case, it would check down because it's saying we do have a big enough sample size. All right, so let me go back to my notes so that way you can see what I just wrote down. All right, so if you kind of notice, I put 10 is greater than or equal to 10 because 10 is equal to 10. So that one does pass that. Well, it does pass the central limit there. But say I have this new event. So let's say this p is equal to 0.02. So if my p is equal to 0.02, is that something that happens fairly regularly, or is that something that like it could take a while before it happens?
It's gonna take a while.
It's gonna take a while. So for this one, do you think the sample size of 40 would still be enough, or do you think we actually need a bigger sample size than 40?
Bigger.
Yeah, so you're gonna need a bigger sample size. So let's say we do a sample size of 40. So we're gonna say 40 times 0.02 times 1 minus 0.02. And let's see, what do we get? So I'm gonna transfer over back to my calculator. So that way you can see how do I enter it. So we'll say 40 times 0.02. And we're gonna multiply that by 1 minus 0.02. All right, if you look at this one, we don't even get 1. So it's telling us a sample size of 40 is not going to be enough in order to see this event occurring. Because if you look at it, if it has a probability of 0.02 chance of occurring, that means if we do this 100 times, we're most likely only going to see 2 times this event occurring. So for this one, we actually need a sample size bigger than 40. Let's see. So what we're gonna do, we're gonna change our n. So we're gonna change our n from 40, and hopefully my mental math is correct. And we're gonna switch this to 2000. So now we're gonna say P is equal to 0.02, N is equal to 2000. So we're saying we have to have a sample size of 2000 in order for this to be approximately normal. So we're gonna say 2000 multiplied by 0.02 multiplied by 1 minus 0.02. All right, so let me go ahead and switch it over. So we'll say 2000 times 0.02 times 1 minus 0.02. If you multiply that out. All right. If you look at it now, we get 39.2. Actually, I think I want it. So if you look at this case scenario, pretty much it's saying we need a bigger sample size to pretty much be able to get something greater than 10. So that's why it's important for, if you know the sample proportion, you do kind of want to know, hey, if you have a P that's less likely to occur, you should know that it's going to take a bigger sample size. But if you have something that happens 50% of the chance, well, 50% of the time, that one you're actually going to need a smaller sample size. So depending on what your P or population proportion is equal to, it should dictate how big or how small the sample size you're going to need. Everybody,
Are
Adam, you have
we
a question?
driving for like a specific sample size closer to 10? Like since that one's so much greater? Or does it matter?
Well, it doesn't matter. Let me see, because the sample size for this one probably, I think I went a little bit overboard, probably just 200 times 0.02 times.
I did it for 500 and that was only 9.8. 600 got us to 11.76. So.
Okay. Yeah, so if you kind of notice, like, once you get to 600, then it finally, like, reaches out. Well, I'm pretty sure this is the other number. Somebody else is giving me 550. But yeah, I pretty much, like, the only thing I want you to get from this is kind of notice, like, your N will kind of depend on what your P or population proportion is. Because the smaller your population proportion is, the bigger your sample size should be getting. But if your if your population proportion is close to 0.50, you're actually going to need like your sample size should be smaller, because for something that happened like half of the time, that's something that you're going to need a smaller sample size. All right, so let's go over back to my notes. All right, so for this one, I'm going to show you how to find the probability. So for the probability, you first want to find the standard error. So when I say standard error, I'm just referring to this value over here. So that's your standard error. Once you find the standard error, what I want you to do, we're going to just skip step number 2. And we're going to get into, you're going to draw it out. So what I want you to do, I want you to draw out the normal distribution. And then what we're gonna do, we're gonna do part 4, where we're gonna find the probability using normal CDF. So once again, we're gonna use normal CDF for this distribution. All right. So let's go ahead and do the first problem, and then I think that should be all the time that we have. So for this one, it said a simple random sample of size n is equal to 200, whose population proportion with a special characteristic is p is equal to 0.75. So I'm telling you the population proportion is equal to 0.75, and I'm telling you n is equal to 200. For this problem, are they telling me the distribution of the sample? Are they telling me it's skewed to the left, skewed to the right, or normal?
No.
No. So for this one, we know it's not normal. So we have to use the central limit theorem to see if we could say it's approximately normal. So first thing we're going to do, we're going to describe the sampling distribution of p hat. So what we're going to go ahead and do, we're going to find mu of p hat. We're going to find sigma of p hat. And then we have to go ahead and do is see if this could be normal, not normal, or we could say it's approximately normal. So if you kind of look at it, it's exactly what we did for the last problem when it says describe the sampling distribution. The only thing different for this one, since we're doing it for the sample proportion and not the sample mean, we do mu of p hat versus doing mu of x bar. Any questions so far for the notation? All right then. So mu of p hat is equal to p. P in this case is 0.75. So you put 0.75 there. All right, and that's it for mu of p hat. Any question for mu of p hat? Okay, let's do sigma of p hat. So sigma of p hat is equal to square root of p times 1 minus p divided by n. So this one going to be square root of 0.75 times 1 minus 0.75, all divided by n, which is 200. And I probably need a little bit more room. Any questions so far? I got square root of 0.75 times 1 minus 0.75 divided by 200. Okay, so I'm going to go ahead and transition over to the TI-84. For that way you can see how I enter it into the TI-84. So you're going to put second x squared. And I'll give you a square root. So you do 0.75 parenthesis 1 minus 0.75 close parenthesis, and you divide this by 200. Any questions so far? I got square root of 0.75 times 1 minus 0.75 divided by 200. So press enter. And my answer should be 0.0306. Usually when you're dealing with decimal or proportion, you want to get 4 decimal places. So always get 4 decimal places for 8.2 for the standard here. All right. So if there's no question in regard to this, I'm going to transition over to my notes. Okay. So up next, we're going to go ahead and see if we could say this distribution is normal, non-normal, or approximately normal. So we already know it's not normal. because our problem, they don't tell us that it has a normal distribution. So they don't pretty much tell us in the beginning. So now the only two options we have is we can either say it's non-normal, or we can say the distribution is approximately normal. So to see if the distribution is approximately normal, we're going to use the central limit theorem. So for the central limit theorem, we're only going to check to see if n times p times 1 minus p is that's greater than or equal to 10. So if you look at n is 200. So say 200 times p, which is 0.75, times 1 minus 0.75. So I'm going to go ahead and you do that on my calculator. So you do 200 times 0.75 multiplied by 1 minus 0.75. And if you look at that, we got 37.5. So 37.5 is indeed bigger than or equal to 10. So this checks out. So that means it's not normal. We're gonna say is approximately normal because it passed the condition of the central limit theorem. And that's it for that part A. Any question in regard to part A? All right, so I'm actually gonna stop it right there and we'll leave that for Wednesday.
I have a question.